Darn it, for Dan. Sorry, Dan, we missed the first part. I'll go back and explain it later. Okay, so here we go. Sine x to the fourth times the sine of x dx. I will break up that fifth degree into a fourth and a sine, setting myself up for a derivative. So if sine is going to become a derivative, the dx part or the du part, then the rest of it has to be written as a composition in terms of cosine. Would you all agree? Because derivative of cosine is minus sine, right? Is there a way? See the logic, what's going on. I pulled this out. Because I had a fifth, I pulled one out. That's an extra one. This guy is going to be my du as I move forward, right? This guy's going to be my derivative part to work with this composition that I have, right? I have a composition. Ideally, we're going to have a u, and then we have a du. But to get the du, we need to change that sine to the fourth into cosines. Kyle, you got an idea?
It would be 1 minus cosine squared of x squared.
Very nice. So sine x to the fourth, some of you guys might have already solved this, can be thought of as sine squared. Would you all agree? Sine squared squared. And what's the beauty of sine squared? Well, the beauty of sine squared comes in when I pull up my sleeve and look at my tattoo, which says sine squared plus cosine squared is 1. This here allows us to swap back and forth between sines and cosines, squares, very easily. And as Kyle said, sine squared can be replaced with 1 minus. You guys see how we can replace it with 1 minus cosine squared. Are you guys all okay with that? Everybody's good with that? So maybe I'm going way too many baby steps, but I want to make sure that this gets into our head. 1 minus cosine squared is going to replace sine squared. And so when we do that, we now have an integral, 1 minus cosine squared with a sine of x dx. What is so nice about that is I now have my composition, right? I'm looking for a composition, but it is rewritten, reformatted, such that I now can assign a u with sine being the derivative. Do you see that? Okay. Nate, what am I going to let you be? Almost. Absolutely. Almost 1 minus cosine squared. You are so close. Very close. We're going to go a little smaller. Just let you be the most inside part, which is going to be cosine. Yes. 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 Absolutely. We're going to go all the way down, and we are going to let you be cosine. Beautiful. I love it. How you're looking on the inside. We're focusing on the inside, but we're drilling down even more far. Are you with me, Reed, right? We have to go all the way down because what's the derivative of cosine? Joel, what's the derivative of cosine? Negative sine. That's where I'm getting my du. Absolutely. Thanks, Nate. Thanks, Joel. Perfect. We got it. There we go. U went all the way down into cosine. When u is cosine, then the derivative appears right here. Does that make sense to everybody? Now, I could do 1 minus cosine squared of x, but that'll get a little complicated because I'll have to take a derivative and it's got a chain rule, and it might get a little complicated. So I want you guys to get used to going all the way down if you can. Some people and some teachers will teach you to, before you assign a u, to actually expand this out. And you can do that if you want to, if that helps you see it better. Because our next step is going to do a replacement and then expand. But if you want to, at this point here, expand first, then assign a u, you can do that. Does that make sense to everybody? Well, I'll show you. Here we go. Everybody's there. Okay, here we go. All right. Did anybody do this out and get an answer for me all the way down at the bottom? Let's see what happens. 1 minus cosine squared. So if I make a substitution, u being cosine, that's going to give me 1 minus u squared. Oh, hang on, Tina, you didn't do the substitution right. You substituted u, but you did not substitute du. So we're going to turn this into negative du. And now I'm going to expand it out. Again, some people will expand it with the cosine. I found that confused some students last time, but if you want, you can expand it out with your cosine and then see your u sub, okay? Or you can do that u sub right away and then expand it out. You get 1 minus 2u squared plus u to the 4th du. And I might do one more thing so I don't lose my negative. I might, at this point, put my negative back in, just so I don't lose it at the very end. I'll push this up for you. So, we do our u, we expand it out, doing foiling. Did I FOIL that right? I think I FOILed that right. And then I get down to my u's, and now all I have to do is take my antiderivative. Alyssa, are you with me so far? You want to give me this antiderivative?
Yeah. It would be negative x.
Negative, help me out with my variable quick.
Of u.
Negative u, thank you. Beautiful.
Plus 2/3 u to the third.
Yep.
Absolutely,
that's what it is. Perfect. And then we go back and we substitute what our u was, and we had chosen u to be cosine. Yeah, Anand, give me what we got here. Negative cosine of x plus, can you see it? Is it low? Can you see it? Plus 2/3. That's a bad position for that board, isn't it? 2/3. I'm just learning that. Cosine cubed of x minus 1/5 cosine of 5th to the x. Plus c. Perfect. How are you guys? When I put things down here, do you have trouble seeing them in the back a little bit? Is it better if I keep it up higher? Probably up higher. Probably I'll keep it up higher, okay? Are you guys okay over there? Okay. Does anybody have questions on how or why we did what we did? So we started with the composition. We didn't have the derivative part, but we used a trig identity to get the derivative part. Are y'all with me? So I'm going to give you one to try. Okay, I'm going to give you one to try. I'm going to wander. That way you can ask me on the example we just did if you had any questions. But you can also try this one here. I want the second integral is going to be the antiderivative of cosine to the 3rd of x dx. Notice composition, right? You see that composition sticking out at you, right? All righty, go to it. Absolutely. You never have to ask. You can just get up and go. Divide it up. Beautiful. Now what are you going to do? Because now you got your derivative, right? Turn the cosine in terms of sine. Yeah, got to change that cosine squared into sines, right? So that you can make your u. Absolutely. Yes. I could throw tangents and secants up there while I'm at it, huh? You guys want some tangents and secants? No, we'll just stay with cosines and sines real slow first. Real slow first till we get going here. It's good. Wait till I combine it. Make it one step up. We'll just go a little slow. We like trig, but we don't like trig that much. How you doing? So that's your derivative. Cosine is a derivative of what function? Of sine. So you need to change him into sines. Does that make logical sense? Good. Change him into sines. What's cosine squared? this, Paul. You good with this? I see you guys are so good. And you got an answer for me. You did good. You see how it works? Absolutely. Don't forget at the bit. Oh, yeah, there's the answer. Yes. No, you good with this? Yes, you are. All right, let me put an answer up so that we don't waste too much time. I think you guys are getting it. I think everybody's getting it. You took your cosine cubed and you changed your cosine cubed into cosine squared times cosine. Why did you do that? Your end goal was to turn this into a derivative, which meant you needed to have u to be in terms of sine. So this is where our trig identity comes into play. Cosine squared is 1 minus sine squared. Then I let u equal sine. Du is cosine. So my integral becomes 1 minus u squared du, which is just u minus 1/3 u cubed plus c, which is sine of x minus 1/3 sine of x cubed plus c. I don't care how you write that. If you want to put things in parentheses and then put the power 3 outside, perfectly good. If you want to instead bring that down and do the shortcut notation, perfectly good. I don't care how you write it. WebWork takes it both ways as well. Any questions? How are you guys? Pretty easy, right? Are you like, okay, Tina, bring it on. I like this. I can do some more. You ready? Any questions? Any questions at all? All right, here we go. Are you like, okay, I'm ready. I am wide awake. It is Friday. I'm set to go. So now we got some funky things. I've got 2 integrals here. Let's skip the bottom one. Let's just go right here to this one. Sine to the 4th of 5x. This one's going to be a nice beast. Oh, yes. Hal's going to wake you up, right? Here you go. You are, absolutely. I'm wired with coffee. I can't seem to get more than 4 hours sleep. How about you?
Oh, no, I'm doing better than that.
Okay. Well, but dang, I'm up here. Like, if you're up here, it keeps you awake much better. If I was sitting right here, I'd be asleep. I swear to God. So I am not going to sit down. No way. Thought patterns. Thought patterns. Now remember, we've got an identity with sine squared and cosine squared in it, right? Okay. Thought patterns, thought patterns. Any ideas, no ideas, really bad. Some ideas are a little easier to work with, but no idea is bad. Thought ideas. What you thinking of doing? What you thinking of doing? Any ideas? We need a derivative, right? Okay, well, first of all, I've got lots of powers of sine and lots of powers of cosine. When you do a derivative, you just want to have one sine or one cosine. Are you with me? What do you think might be an easier way, possibly, to get a single one out there? Yeah, Joel.
Don't you take one of the cosines out?
Yes. Why did you think maybe if I take a cosine out, it'll be easier? Because what happens then? It leaves you with an even power. It leaves you with one cosine, but more importantly, it leaves you with 2 cosines to change into sines if I so need it. Absolutely. Let's take out one cosine. So let's take out one cosine. I love that reasoning. So we've got sine of 5x. I'm going to do it this way, to the 4th power. I'm going to take out one of the cosines. So I'm going to raise this to the 2nd power, but then I'm going to put one of these on the outside just like that. Because this here looks like the setup for an awesome derivative. I think I'm going to let you guys try and finish this. Okay? And I'm going to wander. Instead, when you see only even powers, there was a second identity that I put on the board at the beginning, and I put a little note that said, this comes in handy when you have only even powers. All right, so can you look back in your notes? Or Anna, you got me? What identities did I write down that we're going to use right now? What identities are they? Double angle identities. Can you give the first one to me? It's cosine squared equals
1/2 times 1 minus sine squared.
I'm going to redo it this way. It's actually, make sure this is in your notes the right way. Cosine, yeah, is it good? Yep, good. Cosine squared is 1/2 times 1 plus cosine of 2x. And sine squared is 1/2 times 1 minus, that's where the minus comes in, 1 minus cosine of 2x. So these are what we call double angles identities. You also refer to them as half angle identities, but we in Calc 2 call them our power reducing identities. That's how we refer to these suckers. And power reducing identities work well when we have only even powers on sine and cosine. Notice, we only have an even power on sine, correct? Only an even power. U sub's a no-go. So instead, we're going to use one of these power-reducing identities. Nate, which one are we going to pick?
Probably the sine squared x.
Probably the sine squared x. By logical conclusion, absolutely. We're going to take sine squared and we're going to turn it into this. All right, here we go. Kyle, you turning it in for me? Because you're going to tell me what we get after we turn it in, okay? So let's stick that in there. I'm going to make sure you don't fall asleep either. Here we go. I know, because I'm feeling like I got to go to sleep. Do you guys want to go to sleep? I got a paper to write. Do you guys have papers to write tonight? Oh, my God. Welcome to being a student all over again. All righty. I'm going to soon have real purple stuff under my eyes, right? All right. We changed it. Like Nate said, we changed it from sine squared into 1/2 times 1 minus cosine 2x. All right, Kyle, here we go. We're going to take this antiderivative. What do you want to do? Thoughts? Well, let me ask you. Do you prefer to take the 1/2 out front, or would you like to put the 1/2 in? It's good either way. Put it in front, throw it in front? Okay, so is that what you meant? Or put it in, distribute it in? Pull it right in front. Let's pull that 1/2 in front. I like it. I think that's a great idea to start. It allows us to take a look at what's left over. When it's in there, it makes it a little more complicated, unless you distribute it. If you distribute it, then it's okay. Okay, now, Kyle, are you with me? Still with me, right? Now that we pulled that out, now do you see some good stuff going on? What's the antiderivative of 1? Can we just do that? Yeah, and how about the antiderivative of cos 2x? Can we just do that? Okay, help me out here. So what do we got? 1/2 times. Antiderivative of 1. X. Antiderivative of negative cosine 2x is going to be, this is the tricky with the plus minus thing. Negative. Yep. With absolutely, with the thing in front, right? And because we're doing antiderivative, we're going to flip it over, okay? And hello, there we go, we're done. If you want to multiply it out and make it nice and pretty, you could also write it like this. But heck, man, love those power-reducing formulas. Why do we love those power-reducing formulas? We love those power-reducing formulas because they give us right away a linear function that we can actually take the antiderivative of. This works nice if you have only even powers. Do you see only even powers? Are you with me? How are we? Good? Good? Maybe good? Are we ready? Go ahead, you guys try this one then. You guys try this one. I'll leave all these steps there. I know I went really fast. Can you guys see your practice problem right here in the middle? I kind of want to still leave my work. I need to leave less space, I think. I think I needed to go into my notes and squish these up a little bit. You have the antiderivative of sine squared cosine squared. Antiderivative of sine squared cosine squared. Let's think through it. There's no odd powers. Everything is even, right? Sine squared, cosine squared. I am telling you the easiest way to do this, well, you can either convert sine squared into cosine squared, but the easiest way when I see only evens is I immediately use my power reducing formulas. That's how I would approach it. I would replace sine squared with what it is and cosine squared with what it is. That's how I would work it. You could do it other ways. You could play with some other identities and then use power reducing. But my first instinct, I have this rule that says if it's only evens, I use power reducing, so I would try it that way. That's how I would try it. Are you with me? Yeah. Do you know what that power reducing one is? Let me write it down for us. Let's see. Let me see. So our power reducing formula was, let me write it down. So we had that sine squared of x was 1/2 1 minus cosine of 2x, and we have that cosine squared is 1/2 1 plus cosine 2x. Remember, today we are practicing looking for patterns. When you see all even powers in your integral, you want to think power reducing formulas. So I would probably change sine squared into 1/2 times 1 minus cosine. And then I would change cosine squared into 1/2 times 1 plus cosine. And then I would play with it a little bit. Probably multiply those halves and get a fourth. Maybe distribute and FOIL, first, outer, inner, last. Yeah, I'm going to let you guys do some self-discovery with this one. Because I can do it. I know how to do it. But you guys, I want to go down. Did you get me an answer all the way? Changed it. It was so good. One quick thing. I got so excited I missed it. It's a double angle formula, so it changes from 2x. It changes from x. And it's 2x. Oh! I messed it up. No, I didn't. Because we didn't do all evens up here yet. Because this formula takes this formula takes x and goes to double it. So instead of 2x, yeah, thank you.
Does that turn the 1/2 into 1/4?
It does. Well, yes, this here turns into 1/4. Yes, it does.
No, when you.
Oh, but then FOIL it. Let's FOIL it out. Let's see. How many of you guys are a little stuck? Let's see what we're doing so far. Did you guys get some answers? Okay, let's see where you're at. Okay, so let's see, Anna, to answer your question. So I'm not sure what question you have, but I'm going to do this first. I'm going to take 1/4 and just pull it all out just for a minute. And then I'm left with 1 minus cosine 2x times 1 plus cosine 2x. And if I'm going to multiply this out, okay, let's see. We get 1 minus 1 plus cosine 2x minus cosine 2x, which goes away, minus cosine 2x squared dx. So if I FOIL it out, it actually just becomes 1/4 1 minus cosine squared of 2x dx. Are you with me? Okay. Now, Nate, what did you see here? You don't have to see this, but what did you see here?
You can change the 1 minus cosine squared of 2x into sine squared 2x.
Now, you don't have to, but he said, oh, hey, 1 minus cosine squared is just sine squared. So, I'm going to just put 2 arrows here. You can either do it this way, Nate's way, or you can continue working with the cosine squared. Are you with me? You can continue working and divide this up into 2 integrals, 1 dx and then 1/4 cosine squared of 2x dx, and work with the cosine squared over there. Are you with me? Or you can, if you love trigonometry and you got that tattoo and it's like ingrained, 1 minus cosine squared is just sine squared. Ha. Now, Anna, did I answer your question somewhere? Not yet.
Not yet.
Not yet. Okay, good. Okay, good. So I personally think this is pretty cool. We could separate it, which I have no problem, and we could do that 1,000%. It'll give us the same answer, but this is cleaner. I didn't think of doing it, but I like it. So now I'm going to take sine squared 2x, and I'm going to apply my power reducing formula because it's an even power. So my brain says it's an even power. I'm going to apply this formula up here. But notice I want to highlight what we got here. It goes from a single x to a double x. From a single x to a double x. It grows. Are you with me? Holden, are you with me right now? So, when I go to apply my formula, do you want to give me the formula here, what it becomes? Can you help me out with this? Let's see. So, we got what? We got 1/4 in front. And so it's going to be what? 1/2?
Yeah, 1/2 times the quantity of be 1 minus cosine 2x.
1 minus double that sucker for me. Because the formula doubles him. Do you see how he doubles them here?
Yeah.
So double them for me.
So
Double 2x.
so it would be 4x.
Exactly. Yes, it would be. Yes, it would be. Yes, it would be. Right there. It's going to be 4x because we have to double it. If we had sine squared of 6x, what would have to go over here? Jenna, if it was 6x here, it'd have to be 12x. It doubles it. You guys see that? Megan, you got that, right? Okay, good. Megan, you want to finish this? Are you following me so far? Are you good so far? You want to try it?
I'm good.
No trying. That's okay. That's good. Who wants to try it? Paul, you want to try it for me? No? Lilia, you want to try it? You can say no because everybody's saying no. Everybody said, you can say yes too. Who wants to say yes? Who? Okay, go ahead, Kyle. Give me Kyle. Go ahead, Kyle, and then.
I would take out the 1/2 and have 1/8
Okay.
of the integral that we already have, and then from there I would just then you just anti-drive it from there, and then just 1/8 multiplied by x minus sine to the 4x.
Minus sine.
Oh wait, no,
4x.
Sine.
Of what? Of.
Yeah, well,
Yep. That's exactly what it is. So no matter how you do it, either way, whether you break it up and do cosine squared separate or you put it with this, everybody should be getting 1/8 minus. Did you get that? Yep, good. 1/8 minus 1/32 sine of 4x plus c. I just want to make sure we got that. I'm going to let that sink in for a second. Somewhere in your notes, I don't care where you put them, put the little note that, okay, these formulas, power reducing, work well when you have even power only in your integral, okay? Even power only. How are we? Are we feeling okay? Are we like, okay, Tina, I can do some trig. It's okay. Joel, how are we feeling? Are we okay with these? Yeah? Megan? Okay. Nate? Okay. Yeah, okay. You have to say, okay, right? You can say, no way, Tina, are you kidding me? Just let us out early. Just want to go home and do my homework, dues to noon. All right. Any questions, guys? Any questions? I don't know what's my next integral going to be. Are we going to go to secants and do you want to practice one more even, or you think you guys are good with the evens? Want to do one more even? No? You think you're okay with evens? Okay, we'll come back to the evens next week. Okay, alrighty. So let's do quickly then. Let's move forward and let's look at our summary. All right, so let's summarize what we've learned so far, okay? For odd powers, and the examples that I skipped over, if you guys are following along in your notes, if you downloaded the notes, we'll come back and use those as warm-ups next week, okay? So I left a couple examples. We'll come back and use those next week. We skipped right ahead to the summary in our notes if you've downloaded it from Canvas. We are going to talk about when you have only odd powers of cosine and sine. For example, let me give you well, not only odd powers, but for odd powers. So if I have cosine to the 9th of x, or maybe I have an example, sine to the 7th of x times the cosine cubed of x. Or maybe I even have them mixed up, where I have cosine to the 4th of x with a sine cubed of x. Okay? So let's say I've got some odd powers mixed into my integrals. What is our theory of approach? What do we do? Anna.
Bring a single out so that we can get derivative.
Bring a single out. So which do we focus on? We focus on an odd power, whether it be this odd power, this odd power, this odd power, this odd power. We focus on an odd power and pull out one sine or cosine. So we focus on an odd power. And then we pull out one sine or one cosine. So, for instance, if we have an odd power here, we would pull out a sine. So we'd put a sine x on the side and a sine squared inside. All right, then what's the next step? Then what do we do? Quinn, what do we do then? Yes, you showed me. What do we do? We change everything else.
Yeah,
Go ahead.
Sine squared x. In this case.
Yep.
Change that to 1 minus cosine squared.
So I'll write down, change the opposite trig function using
Plus
1 equals sine squared plus cosine squared. So if we pull out a sine, then we change the rest to be cosines. Change into the opposite trig function, I should say. Change into the opposite trig function. We want to change into cosines. If we pull out a sine, we want to change into cosines. If we pull out a cosine, we want to change into sines. And then we finish with u sub, okay? Then you finish with u sub. If I was taking notes, if I was you, I would put a little highlight, I'd put a little star, and then I would say, work this through as an example after class. Like, I would tell myself, okay, tonight I'm going to go home, I'm going to look at my notes, and I'm going to go through and I'm going to work that through as an example. Do you see what I'm saying? So that I follow and practice that step tonight. Solidify it when you walk out of this classroom, okay? Because it's easy sometimes when you're in class, sometimes when you get out you forget. So tonight I would follow up, I would just put a little follow up outside of class, finish this. You can check your answer on Wolfram Alpha or whatever, okay? I don't know what program you guys use to check your math or do your math, whatever. All right, even powers. For only even powers, what do we use? Alex, what do we use for only even powers? It's the, what do we call those suckers? Power reducing. So if it's only even, we use power reducing formulas. So if it's only even, for instance, cosine to the 4th of 10x dx, or sine squared of x cosine to the 6th of x. Now we use what's called power reducing. I would not challenge myself. I would challenge myself with the top one and try that one outside of class. I wouldn't chew the bottom one. The bottom one's going to be a bear. But use power reducing formulas. That tells me sine squared is 1 minus cosine of 2x times a half, or cosine squared is 1/2 times 1 plus cosine of 2x. The important thing being x doubles in this formula. It's like a double angle thing, okay? That's the important thing. Okay. All right, so that's our quick summary of sines and cosines, allowing us to bump ahead and talk about tangents and secants. All right, tangents and secants. How are we? Good? Okay. Oh, we already wrote these. Well, okay, we didn't do all these. Deli, you haven't talked to me today. Can you give me antiderivative secant squared? I'll give you the easy one. Oh, actually, you can choose. Antiderivative of secant squared, antiderivative of tangent, antiderivative of secant. Which one you want to do? Antiderivative of secant squared is? Thank you. Absolutely is absolutely. Who else have I not? William, I haven't heard from you. Give me antiderivative of tangent.
The antiderivative of tangent is negative after log of cosine.
Thank you.
Value of cosine.
Absolutely. You got it. Wonderful. I got Holden. I got Deli. Jenna gave me some answers. Quinn, did you help me? Yeah, you did. You helped me. Munia, give me an answer. What's the antiderivative of secant?
Natural log of absolute value of secant plus tangent plus c.
Beautiful. Okay, good. Guys, want to have these in your notes, okay? You want to get comfortable looking at these and saying, okay, these are pretty simple. I should be able to do these. They're simple, right? Okay, these are things you're just going to, you're like, oh my God, Tina, don't give me anything else to memorize. I can't remember. I'll bring your formula sheets next week. I do bring formula sheets in for the rest of the trig identities. I mean, the integration techniques, and I can't remember if I put those on there. I might put those on there for you, the antiderivative tangent, antiderivative secant. But for now, let's take a look. So, keeping those in mind, let's talk. Let's talk. Your hand is your hand.
I just switched
Oh,
all the
smart.
time.
Oh, smart. All right, what do we want to do, guys? Thoughts? Anybody have thoughts? Brandon, I didn't get to hear from you yet.
Switch secant squared and just show it with the rest of the answer.
Oh, I like it. I see what you're saying. The antiderivative of secant squared is tangent. Yes, it is. The derivative of tangent is secant squared. Yes. 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 I like your thinking. I like your thinking. You're just thinking. You're thinking, right? You're saying, can I do this? And then you're like, wait, oh, I don't know if I can do that.
Could you use use of?
Could we use use of?
Secant squared is the derivative of tangent.
Because secant squared is the derivative of tangent, then I could let u be exactly. Guys, when you see integrals, I want you to do exactly what you, Brandon, and Holden did. You tried something and you said, oh, let me think about this. And we're going to think a little deeper. And then we think a little deeper, and thinking a little deeper gives us other thoughts. I loved it. You guys did so good. You're a good team. Do you guys do homework together? That would be a good team. That was a good tag team. I loved it. Okay, so here we go. So, secant squared. Did you guys hear what they did? Secant squared is the derivative. It's a derivative. Secant squared is the derivative of tangent. So we're going to just do a u substitution. U equals tangent. Du is secant squared. It's sitting right there in my face. This is my derivative. I'm looking for that derivative. And if I can look to do u substitution, I do it. I'm going to tell you a secret. U substitution is the simplest method in integration. It is the most used integration method in Calc 3, differential equations, and everything higher. You want to get to be experts at u substitution, okay? 1/4. Tangent to the fourth of x plus c. Easy peasy. Lemon squeezy. That's what they say it, right? Easy peasy, lemon squeezy. Have you heard that? Good? Who's got questions? What is it? Easy what? Did you say that? I always mix up my words. So sometimes I make up things. Alrighty. Anybody have questions on the u substitution? You saw the secant squared. Hello, that's a derivative of tangent. Let u be tangent, that's the derivative. U substitution falls out nice into our lap. Aha. Haha. Did I skip some pages? How do I get a summary already? But I guess I get a summary because I want to tell you something. We're going to summarize what we just did really quickly. I don't know why I put this in my notes already. But if you can find a secant secant squared and pull it right here, you're going to do that and use u substitution. Here's another integral. Let's do a different integral. Ready? What if we have this one? Antiderivative of secant to the 7th x tangent x dx. What if I have the antiderivative of secant to the 7th of x tangent of x dx? Now, if I could pull a secant squared out, but then I'm left over with secant to the 5th. Are you with me? And you can't really change secant to the 5th very well. So what might we look at to pull out this time instead of secant squared? I'm getting all my words mixed up. Megan, what might we do this time to pull out instead of secant squared? What might we pull out? Instead of pulling out a secant squared, maybe we can pull out, is that what you were thinking? Pull out a secant tangent. Let's pull the opposite out. What if I have a secant to the 7th, I can break him up as a secant tangent. And if I want that to be my derivative, then what would I let u be, Anand? I would let u then be secant. And do you see how u substitution can be used to solve this one so quick? Did you got this? Do you see this? That's why these are so important, so important. Memorizing these suckers. Yeah, Brandon, give me.
Oh, never mind.
Are you sure?
Yep.
You want to finish it for me? Okay, so you let u be secant, and du becomes secant tangent dx, right?
Yeah, so you just do u to the 6th du, and the integral, that would be u to the 7th over 7, and then you plug it back in, so secant 7 over 7.
Perfect. Nice, nice, nice. You can treat tangents and secants like the sines and cosines, but when you pull something out to use a u substitution, you're going to look for secant squared, turn the rest into tangents, or secant tangent, turn the rest into secants, okay? We'll finish with one more. Last one, and then we're out of here. We got 4 minutes. I think we can do this in 4 minutes. I really do. I think we can do this sucker in 4 minutes. Yeah, I do. Tangent to the 5th of 2x, secant to the 4th of 2x. We're going to use u substitution. I'm going to tell you something really cool. Tangents and secants, these guys, when we mix them up on your tests, you're always going to use a u sub. I'm not going to give you any kind of power reducing for tangents or secants, okay? You'll always use a u substitution. But you're going to have to figure out what you're going to pull out. Are you with me? And what you're going to let u be, okay? So we've got tangent to the 5th, secant to the 4th. Take a second, think about it. And then we'll get it started. We might not finish it, but we'll at least get it started for our notes. While our brains are going and while we're cooking here. We got tangent to the 5th, secant to the 4th. What do you want to pull out to make your derivative? Do you want to pull out a secant squared, or you want to pull out a secant tangent? Can you see that? Can you see that? You're going to sit right up there, huh? Next time. I'm just teasing you. I don't like the way the desks sit in here. It's such a cramped room. It's okay. I don't like how that's there. That's okay. Got ideas? Who has thoughts? Who has thoughts? Who made it work? I think I talked to everybody today. Who has thoughts and wants to give a volunteer and give me a thought? Who's pulling stuff out? Yes. Okay, Lilia, tell me what you pulled out.
I split the secant to the 4 2x to the power of 2.
Thank you. Absolutely. Thank you, Lilia. That's the approach I would use as well. If I can pull out a secant squared and I'm left over with an even power of secant, that's good, because then I can take, hey Derek, then I can take secant squared and I can turn that sucker into tangent squared plus 1 using my identity. So once I pull out secant squared, that means I'm going to have u be tangent. So that means this has to turn into tangents. And I have an identity that allows me to do that. That's the identity tangent squared plus 1 equals secant squared. So that gives me tangent to the 5th times. Secant squared is going to get replaced by tangent squared of 2x plus 1 times secant squared of 2x. And we're out of time. You guys are out of here. But at that point, I would assign u to be tangent of 2x du is 2 secant squared of 2x dx. 1/2 du is secant squared 2x dx, and you are going to integrate u to the 5th times u squared plus 1 times 1/2 du, and I'll let that for you to finish. Hopefully you're going to get the same answer as me. I'm going to skip a zillion steps for you to fill in, right? Skipping a zillion steps. See if you get 1/8 tangent to the 8th of 2x. Ooh, with a half on it. Erase that. Let's try that. 1/16. See, I'm not good at mental math. You guys are going to have to correct me. 1/12 tangent to the 6th of 2x. Did I do that right? Plus c, or did I mess that up? I might have messed that up. Did I mess that up, or that's okay? Are we good here? Guys, have a wonderful weekend. Have fun doing your math. You're working on integration by parts. It's due tonight if you haven't already finished it, okay? Send me emails. I'm going to my office if you want to come by. And you got trig identities, trig integrals to work through. We'll warm up with more trigs on Monday. And we get trig substitution. Oh, yeah. Oh, yeah. I have to give you guys some formulas and some triangles. Have a good day. See you. Bye, guys. See you later. See you soon. Practice the left derivatives. Okay. Perfect. Perfect. I'm going to use the restroom too, so I'll be over after that. See you, Paul. Bye, Kyle. You doing okay? You good? We go a little faster this one. You're good. You're good. You're handling this. You think you're going to be good. Thank you for asking questions yesterday. See you, Patrick. Thank you. Well, 1,000%. It'll take us like 3 minutes. Yeah, I'm going to use the restroom and then I'll be over. So we'll hang up. I'll be over. Natalie, how are you? Good? Yeah. Okay. Hello. Oh, God, I feel you. It's a Friday. God, I just want to. I'm with you, 1,000%. You know, I went home yesterday. I did a power nap last night. In the afternoon at 3 o'clock, I just, boom, crunked out.
Yeah, I take like 20-minute naps.
Yes.
So that way I'm like not tired and like just enough to go.
It is good. Have you ever used the sleep room at Dollar City?
No, typically I'll just like push my.
Yeah. I've never used it. I keep saying the pod. Yeah.
Can you come to 370 for a second, please?
Right now?
Yeah, because I
Yes.
need to.
I think I'm gonna schedule a counseling. Because it's not, it's like, yes, it's important.
iPad?
I do. You can go look. I'm just going to use the
This is
restroom.
nice.
See you later.
Next door.
Next
Next door.
Oh, next door. Oh,
Are you leaving at 45 after? Yeah, I might not see you then.